Hello dear guys. In this video and the next video, we review two important examples of dynamic programming. We finished the concept of deterministic dynamic programming problems with one important example that is in this video, and the video that I will upload soon, I review one example of probabilistic dynamic programming problems. The first example is a very important example to understand the concept of dynamic programming, that its name is local job shop. As you remember in the previous examples, all the items that we had were integer values, okay, and the discrete variables. But as we'll see here, in this example, the state variable is continuous and not restricted to integer values. Let's review the example and try to interpret it. The workload for the local job shop is subject to considerable seasonal fluctuation. However, machine operators are difficult to hire and costly to train, so the manager is reluctant to lay off workers during the slack seasons. Okay, so as you saw, there are seasonal fluctuations, so we don't need a constant level, a fixed level of workers at the different seasons. Okay, so this one will change. He is likewise reluctant to maintain his peak season payroll when it is not required. Furthermore, he is definitely opposed to overtime work on a regular basis. So, as you see here, whatever happens should be happen in a regular time. Since all work is done to custom orders, it is not possible to build up inventories during slack seasons. Therefore, the manager is in a dilemma as to what his policy should be regarding employment levels. So, the manager is interested to know with what number of workloads should follow the seasons: spring, summer, autumn, and winter. Let's go to the next slide to complete this explanation. This table, as you see here, estimates for the minimum employment requirements during the 4 seasons of the year for the foreseeable future. As you see here, guys, when we are saying about the 4 seasons, these four seasons will repeat again and again. So we can limit our example to a period of 4 seasons, okay? As you see here, the minimum requirements for spring is 255, for summer is 220, for autumn is 240, and for winter is 200. And as you see here, this one repeats for spring, summer, autumn, and the winter again and again. So, employment will not be permitted to fall below these levels. So when we are talking about the minimum, it means that, for example, in summer, we are not permitted to have 215, for example. The minimum should be 220. And any employment above these levels is wasted at an approximate cost of 2,000 per person per season. So what is the meaning of that? It means that if instead of, for example, in autumn, instead of 240, we have 250, it means that it's an additional cost of 10 multiplied by 2,000. Okay, so it is estimated that the hiring and firing costs are such that the total cost of changing the level of employment from one season to the next is 200 times the square of the difference in employment levels. So it means that whenever we we move from spring to summer, if we hire or fire, okay, the cost of these two items is $200, okay? So to don't have a problem with the minus in the cost, as you see here, it's a square. So if we name this a period as xn and the previous period xn minus 1, so the cost that this part happens is 200 multiplied by a square of xn minus 1. So fractional levels of employment are possible because of a few part-time employees, and the cost data also apply on a fractional basis. So what is the meaning of that? For example, in winter, instead of having 200, okay, we'll see we have 212.5. So what is the meaning of this 0.5? This 0.5 means the part-time worker that is permitted here in this example. So as we know, these costs, the cost of 2000, okay, and the cost of 200 that we reviewed, form us the total cost. 2000 is the difference with the minimum required, and 200 is the cost of hiring or firing, multiplied by those parentheses that in the next slides we'll see them. So we want in this example to select a policy for employee levels with what end? With the objective of minimizing this total cost of example. Let's try to formulate this one in the next slides and review some other tables. Let's start the formulation of this example. As you saw in the previous table, there were minimum requirements for each of the seasons, spring, summer, autumn, and winter. As you remember, the maximum one was for the spring, that was 255. So based on this numbers in this table, it is not worthwhile and it doesn't have any meaning to have the employment level go above the 255. Okay, so because with maximum 255, if we have all the seasons could work perfectly. Okay, although that this number is not an optimal number, but it's a number that we know that all of the seasons can work properly, because as we know, the minimum of the other seasons is less than 255. So spring employment should be at 255 points. And the problem is reduced to finding the employment level for the other 3 seasons. So because for spring, we need at least 255 and we don't want to have more than 255. So this is the number of employment for the spring. So for the rest of them, we need to find, as you see here, now instead of having 4 x's, x1, x2, x3, and x4, we have 3 x's to make a decision. Okay, so these decisions are for summer, autumn, and winter. For a dynamic programming formulation, the seasons should be the stages, of course, and they are actually an indifferent number of stages because the problem extends into the indefinite future. However, each year begins an identical cycle, and because spring employment is known, it is possible to consider only one cycle of 4 seasons ending with the spring season. So we know the spring, that is 255. So if we name our first season to identify, that is summer, as stage 1, the autumn is stage 2, and the winter is stage 3. And our next stage 4 is spring, that we know that it will help us to obtain the information about the stages 3 and then 2 and then 1. So as you see here in this image, stage 1 is summer, stage 2 is autumn, stage 3 is winter, and stage 4 is spring. As you see here, our decision variable, as we know, is the employment level for stages N, that N is 1, 2, 3, and 4. That we know our level 4 here is our spring, that we know is 255. For sure, if we assume an stage 0, for example, it was our previous spring, that one as well is 255. So let's continue in the next slide. Following the previous slide, let's continue the other notations important for formulation of this example. As you saw in the previous slides and in the table, that for each of these seasons, we need a minimum number of work labors. Okay, it means that less than those numbers is not possible for those seasons. From the other side, we saw that the maximum number possible is 255, that is for spring. That, as you remember, I told you it's not worthwhile to have more than that 255. So the selected number of the employers for each of the seasons should be something between this minimum and this 255 as a maximum. As you see that these requirements are R1 220, sorry, R2 240, R3 200, and R4 255. And we show these minimum employment requirements for stage N with Rn. So the Xn can have a number between Rn, that is the minimum requirement, and 255. So as you see here, for example, for a season like winter, that is 200, this Xn may vary between 200 and 255. So there are many different numbers for the number of employees, but we know one of them give us this cost as a minimum amount. Okay, so as you see here, this is the difference with the previous items. The other items, we had Xn as only one amount, but here we are talking about continuous variables as Xn that moves between Rn and 255 as a maximum. Besides, referring to the cost data given in the problem statement, we have this cost. Guys, the total cost of the this job shop problem is what you see here, 200 multiplied by xn minus 1 square. What is this? It means that this parenthesis shows the cost of hiring or firing, no? Between two items, seasons, no? The summer and the spring, the autumn and the summer, no? That each of them means this difference, and as I told you, this square causes this one always uh, positive, and each of these items is equal to cost equal to 200. So this difference square multiplied by 200, and besides this, the number of each of the stage. For example, if R1 is 220 and Xn we find 230, this is the difference between the minimum and what we decided. No, that is, for example, in this case, 10 multiplied by 2000. So we want to minimize this total cost of the example. And note that the cost at the current stage depends upon only the current decision Xn and the employment in the preceding season. So we should find Xn and Xn minus 1 because Rn is clear, and by these items, by these two items, okay, as an optimal form, we find the minimum cost possible for this example. So the preceding employment level is all the information about the current state of affairs that we need to determine the optimal policy henceforth. Therefore, the state Sn for stage n is Sn, that whatever is available for us in this season is what exactly comes from the previous season. As you see here, when n is equal to 1, Sn is equal to x0, like x4, that is 255. The period 0 that we don't see in our table because we start with our summer, but we know this 255 is for spring that comes to the summer, that we start summer with 255, and for sure when we finish here is the same form. So this relationship is very important. Whatever we have in season n is exactly the decision variable that we made. That what is this decision variable based on the hiring or firing. So when we finish summer, the number that we finish the summer is exactly the availability of the autumn. The finishing of the autumn is exactly the starting of the winter. So Sn, the availability of period n, is equal to the decision variable of the previous slide. Let's continue in the next slide. So to complete the formulation of this example, as we discussed before, our aim is minimizing this cost 200 multiplied by xi minus 1 square plus 2000 multiplied by xi minus ri. No, ri is the minimum, and these are the two consecutive periods. And why 4 from 1 to 4? Because they are identical periods, no? One summer, one autumn, one winter, and one spring. This objective function subject to xi between ri and 255. What is ri? Is a relevant minimum of each of the seasons, and 255, that is the maximum of all of them. And the Fn, Sn, and Xn is this immediate cost that we said before, plus minimum of what comes as from the n plus 1. So this is Fn, Xsn, Xn, 200 multiplied by Xn minus Sn square plus 2000 Xn minus Rn plus F star n plus 1xn, that we know this one is that minimum that we have here in this formula. And as we discussed, Sn, availability of the stage n, is exactly equal to xn minus 1. Okay, what it comes as a decision from the period, previous period. What we make a decision for the autumn, it remains for the that actual season, that for example winter in this small example. So let's go forward with the solution. Before that, let's review one table that we have in the next slide. Let's conclude and wrap up what we learned in the previous slides in this table. As you see here, we should make a decision about 4 different periods: summer, autumn, winter, and spring, that we know about, that is 255. That these Rn are the minimums that we have in our table: 220, 240, 200, and 255. And based on the item that we learned, the xn is a continuous variable that should be between minimum and maximum. This minimum is this one, 240, 200, and the maximum of the all periods is 255 for the spring, and x4 as well is equal to 255. Okay, because it's between 255 and 255, so for sure it's 255. And the possible Sn is xn minus 1. As you remember, the S1 is equal to x0 that we had before is equal to 255, because it comes from the period of spring that we already know that. And this S2, S3, and S4 are the availabilities of the periods 2, 3, and 4. As you see here, guys, always this relation is valid. S2 is equal to x1, Sn equal to xn minus 1, S3 is equal to x2, S4 is equal to x5. Okay, so these are the costs that we are talking about them. No, if we form the formulas of the costs, we have this formula for the period 1, period 2, and period 3, and period 4. As you see here, guys, based on what we talked, we are interested to find x1, x2, and x3. Okay, these are the decision variables that we are searching them. Let's continue with the solution. So, as always, we start with the very last stage of our example. As we made an agreement, this is the spring, okay, of the next year, if we imagine like that, because we know that spring is the number that we need in spring is equal to 255. Based on the table in the previous slide, this is the total cost of the spring for our example. How? When the S4 is between 200 and 255. Okay, why 200? Because this one comes for winter, okay, as we know. So as you see here, this cost in this example, the only item that we don't know is this S4. So by finding this S4, we'll see the cost of spring, like as we have here, okay, to add to the other step in N3 that we see that. But we know that Sn is equal to xn minus 1. So by finding x3, as you see here, is exactly equal to S4. So here, instead of S4, I also can write x3. Okay, so this is the minimum cost, the optimal cost of the level n equal to 4. All these elements that you see here, guys, can be obtained from the table, the previous table that we found. So let's start our n equal to 3. N equal to 3, based on the formula, is the minimum of the cost of the level 3, okay, as you see here, plus a 4-star S4 or X3, the one that we had there. So as I told you, here, instead of S4, I can write X3. Why? Because I repeat, there is a relationship as Sn equal to Xn minus 1. So S4 is equal to X3. So totally, as you see here, the formula for F3 star S3 is equal to this total of cost, 200 multiplied by S3 minus X3 minus S3 square plus 2000 multiplied by X3 minus 200 plus 200 multiplied by 255 minus X3 square. This one is exactly this one, okay? For sure, this S2 can be written as X2, that we'll see. So, as we know in this step, if we refer back to the table of the previous slide, the possible values of S3 are 240 and 255. So we want to find, our aim is find these decision variables. Now here we know is 255. Now the decision variable as X3, we want to know what is that. So one possible solution is to solve this example by a graphical approach, okay, as we learned before in different parts. But one easier solution is to find, as you see here, the minimizing x3 in terms of s3, okay? So by considering s3 to have some fixed but unknown values, so this x3, we will see that is a relationship, that is an equation, something like this, based on s3. So if I want to minimize something, what should I do? The best solution is to derivation of this function. No, I derivate this function based on x3. So to this end, I will change this square to a linear form. No, 400 multiplied by x3 minus s3 plus 2000, because this one is 0 and this part will become 1. This is derivation, and the rest, and put it equal to 0. So all these parts that we have is equal to 0. If I change these items, I will obtain x3 star equal to s3 plus 250 divided by 2. So as you see here, this is the amount of our x3. With what s3s? With the s3s between 240 and 255, okay? So in the next slide, we'll see what happens in the continuing of this solution. As you remember, we calculated sx3 star equal to s3 plus 250 divided by 2. So to know that this value is valid always for these periods, for this period that we have in our table, we should check all the values of S3, okay, that we know that they are between 240 and 255. If all these values are give us between this interval, it means that it is valid for all the period. So we agree that if I check this lower bound and this upper bound, okay, I can make a decision that if all these elements are between this interval or not. Let's check. If I put here 240 plus 250 divided by 2, it's 490 divided by 2 is 245. Yes, it's here. 255 plus 250 divided by 2, I think it will give us 252.2. Yes, it's here. So all the values, okay, all the values of S3 shows us that that works for X3. So the cost based on the formula we had in the previous one, now I can substitute X3 like this, okay, in the formula that we prepared in the previous slide. That is this one plus this one plus this one. If I make it simpler, the F3 star S star will be a formula something like that. And always the cost is S3 plus 255 divided by 2. So the amount of X3 star will be something like this. Like the previous part, we know that S3 is equal to X2, okay? Sn equal to Xn minus 1. So by finding X2, it's exactly meaning putting something like this. So we need to calculate X2 that is in the next slide. In the next stage, that is n equal 2, we'll see what happens. What is the difference with these parts? So now we want to focus on the stage 2. For our stage 2, again, we form our formula of the total cost. As you see here, this one comes from the previous part, and this part that is the immediate is what we calculated in our tables, previous table that we had. So, and this first part, sorry, the second part comes from the previous table. So this is the formula, this part is the formula of the cost of this level. So as we know from that table we found previously, table 11.3, the possible values for S2 are between 220 and 255, and the possible values for X2 are 240 and 255. So, as like the previous part, to find the X2, we should derivate this formula from X2, as you see here, and it gives us this relationship if we simplify this whole formula, and we can calculate our X2 equal to 2S2 plus 240 divided by 3. Again, we should check if this X2 is valid for the whole period, this interval of S2. We should check the different values of this S2. In this level n equal to 2, we'll see there is an exception that I explain it in the next slide. In the previous slide, we calculated X2 with this equation, but I told you there is a point that I should let you know here. So for finding and to understand that every element of X2 is correct in its interval, we should check that for all S2s, all X2s are in its interval. So we know that S2 is between 220 and 255, and X2 should be between 240 and 255. If we check this amounts in our table, we'll see. For example, 220, if I put it here in this formula, it will give me an x2 that is 226.7. As you see here, this 226.7 is not in this interval. If I check it by trial and error, I'll see this one is only valid for when S2 is between 240 and 255. If I put 240 here, it gives me 240. It means that for the period and the interval between 220 and 240, I have one amount, and for 240 and 255, there is another amount, okay, that we'll see in our table. So for the interval between 220 and 240, x2 is 240, that is the desired minimizing value, because for the values less than 240, our x2 is not between its interval, that is 240 and 255. And as we learned here, for the amounts between 240 and 255, the x2 is this amount. So we still need to solve the feasible value of x2 that minimize when s2 between 220 and 240. The key to analyzing the behavior of f2, s2, and x2 over the feasible region for x2, again, is the partial derivative of f2 x2 when s2 is less than 240. As I told you, this 240 is the only amount that is valid for the whole interval between 220 and 250. So the solutions in this stage are two. When S2 is between 220 and 240, as we discussed before, x2 star is equal to 200, and for the interval between 240 and 255, this one is valid. Why? Because if I put 240 here, it's inside the interval of x2. If I put 255 as well, it gives me a result between these two elements. So in my formula, if I substitute the element of x2, I will have two formulas like this and like this. And as you see, the only item that we don't have any information about that is S2, okay? And again, based on the relationship that we found, S2 is equal to X1. What is the relationship? Sn equal to Xn minus 1. So in our next table, that is stage 1, we'll find the item of X1. So based on that, we can calculate all the elements and find the different x's. Let's go. So as we know that Sn is equal to Xn minus 1, so with the same reason, we know that S2 is equal to X1. So I should check the cost of my problem in this stage in two levels, when x1 is between 220 and 240, okay, and when it's between 240 and 255. If I put the formula of f2 star x1 that we found it in the previous part in these two formulas, it gives us this formula for 220 and 240, and this formula for 240 and 255. 55. Let's consider the first one, that is 220 and 240. If I derive this item, I will see that, as we know, S1 is equal to 255. In the very first part of the formulation, we found that. Okay, why? Because with the same item, S1 is equal to X0. X0 is our X spring, and we know that is 255. So for all X1 less than or equal to 240, this derivation is negative. So X1 for this formula is 240, that is minimizing the value of F1, S1, and X1 over the region 220 and 240. Based on this number of X1 and S1, we can calculate this equality. If we calculate this one from this side, it gives us $200,000. In the next slide, we should check this item. If it gives us a better cost, we should select this one because we want to minimize the cost. We are interested in the cost that is less than the other one. That is the minimum among others. Let's review the case that is 240 and 255. Again, with the same logic of the previous slide, now we should focus on this part when X1 is between 240 and 255. Again, for considering and finding the X1, we should make a derivation of the formula of the cost that we had in our table. As you see here, based on the levels of Sn that we know, S1 that we know it's 255, X1 is equal to 247.5. Okay, the derivation, this derivation is always positive as well, because S1 is 255. So if I substitute 255 in this formula, that is our X1, X1 is 274.5. Okay, so easily by substituting 247.5 in my formula of the table, okay, the formula that I have in my table, the total cost is $185,000, while the other cost, the X1 between 220 and 240 was $200,000. That this cost is less than that one. So it means that my X1 is equal to 247.5 with a total cost of $185,000 in a consecutive form with the relationship of Sn equal to Xn minus 1. We can find the different other x's and solve the example. Finally, as I told you, by tracking back through the tables for n equal to 2, 3, and 4, and setting that I told you Sn is equal to Xn star minus 1, each time the resulting optimal solution can be found. As we saw, X1 star was 247.5. So that X1 star is equal to S2. So in the formula of X2 star, that it's only relies on S2, I should put S2 equal to 247.5. That it gives me X2 equal to 245. With the same item, we can calculate X3 star, that is 245.5, and we knew that X4 is 245, with a total estimated cost per cycle of $185,000 that you saw in the table when stage is n equal to 1.